Good afternoon, I'm Laura Foote and today we're going to be looking at probability. This is part 2 and some of the basics were covered in part 1. Today we're going to be looking at independent events, contingency tables and tree diagrams, some of your favorites. First of all, what is an independent event? Basically, an independent event is when you've got two events happening that do not affect each other. So you've basically got two things that are totally unrelated. So for example, I might be throwing a dice and I might be also pulling cards. And if I threw a 6, would it affect which card I drew from a pack of cards? No, not likely. So therefore, these are called independent because they're not related to each other. Hence the word independent events. So when I've got two events happening, the general formula, although I would say that using some of the tables and some of the tree diagrams is a bit more useful, the general formula is that if I've got the probability of something happening and something else happening, that we usually take the probability of that one thing and we times it by the probability of another thing. So I'm going to show you some examples of those so that you can actually understand in real sums what they actually mean. Okay, so for example, if a fair dice is thrown twice, what is the probability of getting a 2 on the first throw and a 4 on the second throw? So we've got a 2 on the first throw and a 4 on the second throw. So what are the chances? Let's think first of all, what are we actually trying to find out? So the probability of a 2 and a 4. Okay, now if I'm throwing the dice twice, does it actually affect each other? If I threw a 2 the first time, would it actually affect whether I could get a 2 again? No. So therefore they are independent events. They do not affect each other. So therefore, I would then find out what is the probability of getting a 2, and I would times it by the probability of getting a 4. Okay, so let's think back to our basic probability. If I've got a fair dice, how many faces does a fair dice have? A fair dice has 6 faces. How many of those faces are a 2? I've only got one face, that is a 2. So if I threw my dice, what are the chances of getting a 2? It's going to be 1 out of 6. Okay, and the same if I've got a fair dice and I'm looking to find out what are my probability of getting a 4? How many faces of my fair dice are a 4? It's only 1 out of the 6 faces. And note I'm now timesing. Now if you're not very good at fractions, I suggest at this point that you get your calculator out and you do it on your calculator. Most people these days have a natural display calculator and you can actually type in the equation or the fraction as you would see it. So it would be 1 over 6 times by 1 over 6 equals 1 over 36, as our calculator says over there. Now, I know that most of you would think that's an easy sum and I can do that in my head. And if you can, that's wonderful. But sometimes it's actually worth getting your calculator out and doing it on your calculator so you don't lose that vital 1 mark that actually could be the difference between an A and a B maybe. Right, let's have a look at example 2. If you toss a coin and roll a dice, what is the probability of getting a tail on the coin and a 6 on the dice? Well, as you can see, we've got 2 individual things happening. So therefore they are independent events. Right, what are we actually looking for? We're looking for a tail and a 6. Okay, so let's write it out as we would in our exam papers. So what is the probability of a tail and a 6. So as our little formula showed us, that we need to find out what is the probability of getting a tail times the probability of getting a 6. What is the probability of getting a tail? Now, if I've got a coin, it's got two faces, a head and a tail. So if I've got two possible outcomes, and one of them is a head and one of them is a tail, then obviously my probability of getting a tail is going to be 1 out of 2. Okay? And similar to the questions that we've done in the previous question, what is the probability of getting a 6? A 6, there's only one face of our die that is actually a 6, so it's going to be 1 out of 6. Now, the last question we use the calculator to actually solve this. This time, let's have a look. If we are multiplying fractions, we times our tops together, or our numerators together, and then we times the bottoms together, which are our denominators. And if I say 1 times 1, I'll get 1, and 2 times 6 is 12. So our answer should be 1/12. We're going on to contingency tables. Now, basically, contingency tables are a way of representing all possible outcomes about two variables. And you'll see that we actually will use a table in order to actually put all our options onto a table, so it's very much easier for us to actually look at probability. We must also be able to calculate the probability of a single event, more than one event, and the possibility of an event not happening. Now, all of these were covered in the previous episode, so we need to be able to apply that information to these new questions. Let's start off by doing a contingency table, as I'm sure most of you have done one before, but the word contingency table probably is a bit confusing. Let's have a look at example 3. At a Gamblers Anonymous rally, 120 gamblers attended. 109 men and 11 women were asked whether they gambled at casinos or played the horses. Of the men, 75 played at horse racing, and 34 gambled at casinos. 8 women gambled at casinos, while 3 bet on horses. Right, now we need to look at all of this information. There's a lot of information there, and we need to actually focus on what information can we use. Right, now the most important bit of information is that there were 120 gamblers at this meeting, or this rally, and that is going to be our total. We have got 120 people altogether. And we need to also then look at the two different variables that we've got. We've got men, we've got women, and we've got people that play at the casinos, and we've got people that go to the horses or bet on the horses. When we come to have to fill in our information on our contingency table, we need to actually decide how are we going to design all this information into our table. So we need to have totals. So I'm going to have a total here and a total there. And my two different variables. It was either going to be men and women, and horses and casinos. Now, if I had put these in opposite directions or swapped them around, it would not change my overall table. It would actually make it exactly the same. So obviously the numbers will be in different places, but the actual numbers, if you had to go to the same column and row that matched together to give, for example, horses and women, it would still give you the same number. So that is not really an issue. You need to make sure that you've got your two different variables on different axes or different sides of your table, and you need to make sure that you've got the two different options that match together. You will need to have totals so that you can actually check that you've actually done this correctly. Now, we've decided, or we've read, that there was 120 people altogether. So if I've got 120 people altogether, My total over here is going to be 120. I've got 120 people that bet on horses and casinos, and I've also got 120 men and women altogether. Now this is quite a nice example because it actually tells us quite a lot of information. They've told us that there were 109 men and 11 women altogether. So if I go to the total of men and total of women, I will get 100, check, let's make sure we're getting this right, 109 and 11, 109 and 11. Now, one thing that you need to make sure that when I add these two numbers up, they do add up to the total. If they do not add up to the total, it should ring a bell in your head that you've actually done something wrong. So go back and check. Right, so 109 and 11 adds up to 120, so that's perfect. We know that we've done that part right. And then it said, of the men. Okay, so we're looking at the men's row or column, depending on how we've drawn up our table. In this scenario, you can see that I've got men, and so my two numbers would go into this section over here. So let's go back. Of the men, 75 played at the horse racing and 34 gambled at the casinos. So we've got 75 at the horses and 34 at the casinos. And again, check with your calculator if you need to. If they're horrible numbers, go back and check. And 75 plus 34 should add up to 109. We have 11 women altogether, and they've told us that 8 gambled at the casinos and 3 bet on the horses. So 8 at the casinos and 3 at the horses. So that should actually be adding up to 11, which is perfect. And just go back and check that you've actually filled in the right information in the right slots. Right, once I've got all of this information into my table, I'm now going to add up to make sure that these all add to 120 again. So this should be 78. 75 plus 3 is 78. 34 plus 8 is 42. And if I add those two together, I should get 120 again. So that's my total. Again, if you're not sure, make sure that you are checking on your calculator. There's no marks for making careless mistakes. Right, now that was the easy part. Now you have to answer some questions about this calculations. So you're now going to use your table, so don't make up your answers. You're going to have to use the information that you've already got in your table now to calculate the probability a gambler chosen randomly is female. Now they're talking about gamblers, they're talking about the whole group. So therefore we need to look at, this is the whole group, the whole rally. So what are the chances that a gambler chosen randomly, they always say chosen randomly because if they were in a crowd and you went and just picked one out, what are the chances that they would be female? Okay, so now I need to go look at my table. Probability, as we've said before, is always a fraction, a decimal. So we need to actually then have this as a fraction. So how many of these gamblers at this rally were female? Well, I remember that there was 11. There's 11 women that were at the rally out of the whole group, which is 120 people. So use your table to calculate the probability that a gambler chosen randomly is a female is going to be 11 out of 120. Okay, that means that you've actually got only 11 people that are women out of the whole group of gamblers of 120 people. Right, let's go on to the next question. It says, calculate the probability that a female gambler, chosen at random, gambles at a casino. Now, this is where they start to try and catch you out. They are talking about only the female gamblers. Now, how many female gamblers did we have? we only had 11. So therefore our denominator has to be 11 because the total number of females is 11. So therefore, if I chose one of those 11 women at random, what are the chances that they gambled at a casino? So let's go look at our table and see how many women gambled at a casino. It was 8 of them. So therefore, 8 out of 11 is my probability that I will get a female gambler that is gambling in a casino. So can you see, very different from the first question, because the first question was talking about the whole group and the second question was talking about just the females in the group. Right, let's see what the next question has to offer us. Calculate the probability a person, okay, person meaning anybody, so the whole group, chosen randomly, played the horses. So out of our whole group, how many were in our whole group? Let's go back and check in our thing. Our whole group was 120 people. So we know our denominator is going to be 120. So what is the probability that a person chosen randomly played the horses? So how many of those people in the whole group played the horses? Okay, horses, we have to go to the end of this row, and it's going to be 78 people. Okay, so it's going to be 78 out of 120. Now, sometimes it's a good idea to convert that 78 out of 120 to a simpler fraction. And again, I would get my calculator out and use my function of fractions and go 78 over 120. And magic's magic, it simplifies it for you. And I get a simplified answer of 13 out of 20. Right, let's go into the next one. What is the probability of a person chosen at random not playing the horses? And the key word is not. Okay, so if they are not playing the horses, then obviously it is the opposite of playing the horses. So generally speaking, if I am not doing something, the formula is that it will be 1 minus the probability of doing it. Okay, so in this case, it would be 1 minus the probability of playing the horses. And as you can see in the previous question, we were playing the horses and we had 78 out of 120 people. So it's basically going to be 1 minus 78 over 120. Again, you can use your calculator, but you should also be able to see very clearly that if 78 played the horses and there were 120 people altogether, we can go back to our table and say, okay, if 78 played the horses, 42 people didn't play the horses. And therefore, our answer should be 42 out of 120. And 42 out of 120 can be simplified to be 7 out of 20. What you will notice very clearly is that this plus that will end up being one whole. So 13 out of 20 and 7 out of 20 will add up to be 20 out of 20, which means that that will be the whole group of people. And that is another way of checking that you've actually done the correct answer. Because obviously, if I've got 120 people, the people that weren't playing the horses and the people that were playing the horses should add up to be your whole group, because those were the only two options they had. Right, let's try something a little bit different. Let's go on to the next example. We're going to be looking at tree diagrams next. This is probably people's worst nightmares, but actually you're going to see that they actually aren't that bad. Generally, for those of you that were a little bit unsure, you have a diagram that looks something like this, And basically, it's a way of showing all your different possible outcomes. So for example, if I tossed a coin, I could have a head and a tail. And if I tossed it again, my options would be a head and a tail again. And obviously, if I got a head first, I could get another head, or I could have got a head and a tail. And the second time I threw it, I could have got first have had a tail, and then the next time had a head. So these are all my different possible answers. I could have got a head and a head, head and a tail and a head, or a tail and a tail. And you can see then that I've got 4 outcomes. Okay, so that's actually a very clear way of actually building up a table in order to find out what are my possible things that could actually happen. And this is very useful in some scenarios where, for example, they do affect each other. They're not independent events. For example, if I'm pulling marbles out of a bag and the number is dropping. So it's easy then to see what is my probability of something happening when I've done certain activities. But we're not going to go on to those harder examples just yet. So let's look at some basics. Right, let's look at example 4. A couple has 2 children. Use a tree diagram to calculate the probability that both children are girls and that the couple has a boy and a girl. Okay, so they say use a tree diagram, but there's no tree diagram here, so that means that it's up to you to actually draw that tree diagram. So let's have a look. What are we going to do first? We need to decide what are our different options. Now, if I have a child, the options are either they're going to be a boy or a girl. So my first child is either going to be a boy or a girl. Okay, now the probability, generally speaking, is I've got half a chance of getting a boy and half a chance of getting a girl. The second child, I still have the same choices. I've still got the chance of getting a boy or a girl and a boy and a girl. Okay, you will always notice that the second choice is the same and it's duplicated for the second chances. So therefore, the first child, you've just got 1 branch split into 2, and the next time you've got 2 branches that are split into 2, because each of those children then will have 1 option each. So therefore, I can get a boy and a boy and a girl and a boy, or a girl and a girl. Those are my possibilities if I've got 2 children. Obviously, if I had 3 children, I'd have a lot more different possible combinations. But we're just focusing with 2 children at the moment. So it says, what are the possibility of both children are girls? Okay, now I have got half a chance here and another half a chance there. Another half a chance there, another half a chance there. And remember that each of these branches has to add up to a whole. So this section, these 2 add up to a whole. That section, those 2 have to add up to a whole. And this section, these 2 have to add up to a whole. So therefore you can actually see that you've actually got all the people that you need to consider, or all the options you need to consider. Now I want the combination of girl and girl. And again, remember the AND rule, that if I want something and something else, I need to multiply my 2 probabilities. I know the probability of getting a girl the first time was half, and I know the probability of getting a girl the second time is also half. So the probability of getting a girl and a girl is equal to the probability of a girl times the probability of a girl. And you can see that that's going to be a half times a half, which is equal to a quarter. Okay. What you do need to remember is that when you go along the branches, you need to multiply. And that is the most important rule, is that when I want to find out what are the chances of getting a girl and a girl, I need to go from this one to that one and times the probabilities. Right, let's move down a little bit. Right, the couple has a boy and a girl. Okay, now I could have quite a few different versions of a boy and a girl. Well, actually I could have a boy and then a girl. Or I could have a girl and a boy. So it doesn't say what order, they just said a boy and a girl. So what are the chances? You can see that there are 4 possible outcomes, and of those 4 possible outcomes, 2 satisfy these criteria. So I can have a boy and a girl going like this, or a girl and a boy doing like that. And you can see that because we worked out that to have 2 girls is a quarter, you'll see that all of these have got a quarter of a chance. And to get a boy and a girl and a boy will be a quarter plus a quarter. Note, it's plus and not multiply. Okay, because once I've gone along my branches, I need to remember that if I've got more than one combination that satisfies that option, I need to then add those possibilities. So I want to add a quarter and a quarter, and a quarter and a quarter is 2 quarters, which can be simplified to be a half. And you can see you have got half a chance. 2 out of the 4 options are a boy and a girl. The order might be different, so I might have had a boy first and then a girl second, or I could have had a girl first and then a boy second. And therefore I've got half a chance of having 2 children of different sex. Right, this is another contingency table. Again, lots of information you need to read carefully. In a global youth tobacco survey, 1,071 current smokers are asked whether they bought their own cigarettes or got somebody else to buy cigarettes for them. Of the 695 males surveyed, 592 bought their own cigarettes. 94 of the youth who got someone else to buy their cigarettes were female. So there's a lot of information, and you need to really be careful about how you read these bits of information. But let's look at our contingency table first and make sure we've got the correct headings, because if we haven't got the correct headings, we've got no hope of actually making sure we've got the whole scenario. So I always start with putting in my total so I don't forget that. And let's look at our 2 different variables. Okay, has it got anything to do with cigarettes? No. But that's where they try and catch you, because most people would have cigarettes and no cigarettes or something like that written in there somewhere. They've told us that there is 1,071 people that they asked. So this is our whole group. Okay, so that's going to be our total of our totals is 1,071. Let me just check that I've correctly written that down, 1,071, because if I haven't written that correctly down, then obviously all my totals are not going to work out properly. Right, now what other options have I got? They talk about males and females, so that would obviously be one of my column or row headings. And what is the other one? Now this isn't an easy one to see, so you need to read it maybe a little bit more carefully again. So they either bought their own cigarettes or got somebody else to buy the cigarettes for them. Very long-winded, so let's make an abbreviation of that. So bought own, or someone else bought. And I've got all male and female. Okay, so those are headings. Now it should be a little bit easier to sort this information into bits that we do know and we don't know. Right, so let's fill in first of all what they've given us. Then it makes it a little bit easier to work out the bits that are missing. Right, of the 695 males, which means that the total of the males is 695. So if I go to my contingency table, if I go to the total column, I should write there 695. Again, make sure that you've checked that is exactly the number that you've actually been given, so that you know that you haven't made any silly mistake. Okay, what other information have they given us? They said of those 695 males, 592 bought their own cigarettes. So now we need to go, they're still males, and they bought their own, and they were 592. Okay, so 592 males bought their own cigarettes. Okay, let's go on to the next bit of information that they've given us. Always just look for the numbers. The numbers actually are the bits that they've given you, so then you can start to try and figure out where they all belong. Then I've got 94 of the youth who got someone else to buy their cigarettes for them were female. It says 94 of the youth who got someone else to buy their cigarettes. Okay, so in the column or the row, someone else bought them. So we're going to be looking in this area. 94 of those people were female. Okay, again, just do a quick check. 94 of the youth who got someone else to buy the cigarettes for them were female. Okay, now there doesn't look like there's very much information there. There looks like a lot of blank boxes. So how are we going to find out what the missing numbers are? And it's a very basic situation here where you actually are using basic concepts of maths and adding and subtracting. Let's change our color of our pen so that we can actually see which bits of information we've added in. Now, how am I going to work out how many females there were? Now, if I've got 695 males and my total is 1,071, then obviously the number of females is going to be the total, take away the number of males. And if we do that on our calculator to make life a little bit easier, I go 1,071 minus my 695, and I get 376 females. I now know that the total number of females is 376, and I know that 94 of them got somebody else to buy their cigarettes for them. So how many of them would have actually bought their own? Now, the easiest way, again, is to get our calculator out. We've got our 376 there already, and I want to actually find out what is the missing number. So I need to take off my 94, and I end up with 282. So I've got 282 women or females who bought their own cigarettes, and I've got 94 that got somebody else to buy them for them. Right, now we need to work out how many males got somebody else to buy their cigarettes for them. Can anybody see how we're going to do this? Yes, again, we're going to take our total and take away the ones that bought their own. So we're going to say 695 minus, let's have a quick check what this number is, 592. And that means we've got 103 males that got somebody else to buy their cigarettes. Now, if we add these columns, we can see what our new totals are. This is quite a nice easy one to add up by yourself without a calculator. 197. This one should be 417, 874. Now again, what I would do is, because I've calculated these two using my own head, I would then take my calculator and do a quick check that I've actually calculated correctly. So this was 874, 874 plus 197. And what answer are you expecting? Yes, it should be this 1071. If you got that answer, then obviously you've added or taken away correctly. Well done. Right, now that again is the easy part. Now they start asking you questions to do with probability. So let's have a look and see if we can figure out what they're actually asking us. So what's the probability that a current smoker chosen randomly, okay, in other words, they're chosen just out of a hat or not in any specific way, and you got somebody else to buy their cigarettes for them. So we're now looking at the whole group. Again, we're looking at the whole group. So this is my whole group here. And whoever we are looking at as the whole group of people that we're looking at has to be the denominator. That is your bottom number of your fractions. So we're looking at our whole group, so I know that the bottom number over here has to be 1071. Okay, now we're going to look at got someone else to buy the cigarettes for them. Okay, which row or column are we going to look at? Somebody else bought them for them. 197 people got somebody else to buy them for them. So that needs to be our numerator, 197. So that is my final answer, 197 out of 1071. You could convert that to be a decimal or a simplified fraction. I don't think there is. Well, we can check. Shall we check if we can simplify this fraction? The easiest way of doing that is to go 197 over 1071, push equals, and you can see that the answers are identical, so it doesn't need to be simplified. If I wanted to change it to be a decimal, I could go S to D, and then I would actually make sure that I had the right number of decimal places that I wanted to round it to. So I could, for example, round that to 0.18 if I wanted to 2 decimal places. Please read carefully in your questions and your question paper about how many decimal places and what formats they would like your answer in. Generally speaking, I would leave it as a fraction, because then the examiners can actually see what you were looking at, what part of the table you used, and it's much easier for them to actually identify whether you have got that answer right or wrong. Right, next question is, so what are the chances of them being a male and got someone else to buy their cigarettes? So out of the whole group again, they had to be male and somebody else bought their cigarettes. Okay, so which part of my table tells me this information? Let's use a highlighter pen so we can see it clearly. They're male and got somebody else to buy their cigarettes. Must be this one over here, 103. Now what is my denominator going to be? What is my bottom number going to be? It's going to be how many people we asked altogether. Now how many people did we ask altogether? Again, it's my whole group. So my top number is going to be 103 out of total of 1071. Right, now be careful. The next ones are a little bit more tricky. It says from the females. So that means that we need to have the bottom number of our things is the total females. Okay, not our total of the whole group. So from the females, that buy their own cigarettes. So own cigarettes over the number of females. Obviously this is the females that bought their own cigarettes. So where would we get this information? Go back. My total number of females is 376, so that needs to be my denominator. And how many of those females bought their own? 282. Now I know, because they're both even numbers, that that number can be simplified. So again, I can get onto my calculator and see what it would be. 282 over 376, push my equals, and that tells me that 3/4 of the women bought their own cigarettes. From those who buy their own cigarettes, how many are females? Okay, can you see that it sounds almost the same, but it's definitely not the same question. So it says, from those who buy their own cigarettes. Okay, now we're going to have to look at a different group of people. So the people that bought their own cigarettes. Okay, let's try a different color. People that bought their own cigarettes. How many people bought their own cigarettes? It was 874 people. So that has to be my denominator. That's my bottom number. That's how many people altogether bought their own cigarettes. Let's write our denominator. 374. Check that no, it's actually 874. It's always a good idea to check. And now we're looking for, of those 874 people, how many were female? And you can see I've already put a little circle around it. So it's going to be 282. 282 people out of the 874 that actually bought their own cigarettes were female. And you can check that by looking at the whole table. So 282 out of 874 is my answer. Okay, so you can see it's quite a different answer. Even though they've got the same 282, the group that you're actually looking at has changed. So therefore your denominator's changed. Your numerator might not have changed, but your denominator will have changed. And again, I can simplify my fraction by going 282 over 874. And that can be simplified to be 141 over 437. Okay, it's not always necessary to simplify your fractions, but it's always a good habit to get into. Right, let's go on to example 6. Tabo and Steve work together at night as night watchmen at a school. The probability of finding Tabo sleeping while at work is 1/5, and that of finding Steve sleeping at the job is 1/4. Right, now basically they've given us fractions already, and we need to then look at the next question, which says, what is the probability of finding Tabo awake? Now they haven't given us any information about him being awake, but obviously if he's not sleeping, he must be awake. So therefore the opposite, or the complementary fraction, that is the opposite of him being asleep. So him being asleep, Tabo sleeping, Tabo sleeping while at work is 1/5. So what are the chances of him not being sleeping? In other words, awake. So the probability of him being awake is going to be equal to 1 minus the probability of him sleeping. Okay, 1 being a whole, so therefore it's going to be 1 take away the chance of him sleeping is 1/5. So 1 minus 1/5, 1 could be written as 5/5. Take away 1/5 is going to be equal to 4/5. Again, if you're not happy about that maths, then use your calculator. Don't make careless mistakes to throw away marks. And you should find that he's either going to be sleeping or awake, and if he's sleeping for 1/5 of the time, then he must be awake for 4/5 of the time. Okay, now the next thing that they want you to do is to draw a tree diagram to illustrate this information. Okay, so what information do they want us to record? They've got two different watchmen. We've got Tabo and we've got Steve. And the information that we are recording is that either they are asleep or they're going to be awake. Okay. Okay, exactly the same as the other probability tree diagrams we've drawn. Can you see that they've got the same options for each of these two branches? So he can either be asleep first, and then Steve still has the option of being asleep or awake, or Tabo can be awake, and then Steve can be either asleep or awake. Right, now let's fill in the information that we know. Okay, we know that Tabo slept at work 1/5 of the time, so he was asleep 1/5, and we've just worked out that he was awake 4/5. And again, like I said earlier, that these two numbers should add up to one whole, because obviously those are the two options. If there were three options, all three of those would have to add up to a whole too. Right, and then we've got Steve. Okay, he's totally separate to Tabo, so his information is totally different. We need to go and look it up. He slept 1/4 of the time at work, so we need to fill in that Steve was 1/4, and that information would be identical at the bottom as well. And then obviously if he slept for 1/4 of the time at work, then he must have been awake for 3/4, because 3/4 and 1/4 adds up to be a whole. So 3/4 at the bottom and 1/4 at the top. So we've drawn our tree diagram to illustrate this information, and if we look on the next page, we'll see that there's questions that actually are related to this. Right. The first question is not related really to the tree diagram, but you can see that it is useful to actually use a tree diagram to decide that. Is Steve sleeping on the job dependent on Tabo sleeping on the job? Explain. Now I know that lots of you, when you come to do maths, explaining is the hardest part. So let's think about it. Is Steve sleeping on the job dependent on Tabo sleeping on the job? Do you think that if the one sleeps, the other's going to sleep too? No, not necessarily. Okay, and that is mainly because if one is sleeping, then the other one doesn't have to sleep. So they both their own people, and they don't have to sleep at the same time. Don't have to sleep at the same time. Okay, so if one slept at one time and the other slept at another time, they wouldn't be sleeping together. Right, how many different combinations are there? Okay, let's go back to our tree diagram and let's have a look. Okay, so we can either have Tabo asleep and Steve asleep, or we can have Tabo asleep and then Steve awake, or we could have Tabo asleep and Tabo awake and Steve asleep, or we can have them both awake. Okay, so there's 1, 2, 3, 4 different possible combinations. And sometimes in the exam question they will ask you to write those out, and in this case you could say Steve asleep, Tabo awake, and you could do all the 4 different combinations that there are. Okay, I'm not going to do that because it just takes up time. Okay, and the next one says, use the tree diagram to determine the probability of an intruder finding both of them asleep. Okay, so that's the most unsuitable scenario when you've got two watchmen. They both are asleep. So we need to go back to our tree diagram and look at, obviously there was only one combination of them both being asleep, asleep and asleep. This is the top one here. And in order to work out what is the probability of them both being asleep, you need to work out the probability of one being asleep times the probability of the other one being asleep. So let's do that. So the probability of Steve being asleep times the probability of Tabo being asleep. And hopefully that time isn't very high. Okay, so going back. So Steve being asleep was a quarter and Tabo being asleep is a fifth. So it would be a fifth times a quarter. Or a quarter times a fifth. It doesn't really matter which way around you write it, because you are multiplying, and if I'm multiplying, I times my numerators together and my denominators together, and so it's 1/20th of a chance, which is reasonably low. So 1/20th of the chance that they'll both be asleep. Okay, so what is the probability of them both being awake? So this one is going to be Steve awake, and, which means times, Tabo awake, and it's going to be the opposite of these ones. So it's going to be 3/4 times 4/5, and we can check that on our tree diagram. Both of them being awake, awake and awake, 4/5, 3/4. Because we're going down a branch, we're multiplying. Okay, so times these together, it's going to be 12/20. Right, now, is that what you expected? Surely if they were not asleep, then they should have been all awake, and these two numbers should have added up to 20/20. Why don't they? 12/20 plus 1/20 is 13/20. That doesn't seem right, but it is. It is right, and the reason why it's right is that there are two other possible combinations, and we look back on our tree diagram, you can see that there's other combinations of one of them being asleep and one being awake, and vice versa. So they don't have to. But if I'd worked out all the different combinations and their probabilities, then yes, all four of those possible combinations had to add up to be 20/20. Okay, so before we'd looked at gamblers and non-gamblers or things like that, and they did add up because there were only two different possible answers. In this scenario, there's a lot more combinations, so therefore not necessarily if they're awake or both asleep, it will add up to 20/20. So don't stress about that. Okay, so 12/20, and that could be simplified to be 6/10 or 3/5. So 3/5 of a chance that you've actually got both of them awake, which is a bonus. Okay, what are the chances of only Steve being asleep? Okay, so the combination then would be obviously that Tabo is awake and Steve is asleep. And if we look back at our tree diagram, we can see, okay, what is the combinations where Steve is awake? Let's just check our question again. Sorry, going back instead of forward. Okay, we want only Steve asleep. Okay, check our tree diagram, only Steve asleep. Okay, it's either this one. No, it can't be this one. It can't be that one because there Taba's asleep too. This one, where Steve's asleep, Taba's awake. So it's this combination. So it's going to be Taba awake and Steve asleep. So it's going to be 4/5 times 1/4. So let's do that as our combination. Four fifths times 1/4. Okay. 4/5 times 1/4 is going to be 4 out of 20, which can be simplified to be 1 out of 5. So 1/5 of a chance that Steve will only be asleep and Taba will be awake. Right, hopefully all of you are seeing how easy these can actually be if you read the question correctly and you actually look carefully at the tables and the graphs and the tree diagrams that you've actually drawn. Okay, let's look at one more example. Example number 7. Right, now often, instead of getting you to draw the contingency table, they actually will give you a contingency table with all the data that you actually need. So in this table, this shows the data of non-natural deaths in South Africa during the first 6 months of 1999. Okay, you can see from this information, there's the ages of the people at the top, and then the types of deaths that are unnatural along the side. Okay, now all you're needing to do now is read carefully. You need to find out what is your numerator and what is your denominator. Okay, let's have a look at the first question. What's the probability that a child between the age of 10 and 14, chosen randomly, would have been a suicide victim? So we need to look and see where are my two columns meeting. So age 10 to 14 and suicide. 10 to 14, suicide, there were 6. And we're talking about any person, the probability of a child chosen at random, which means that we're looking at the whole group, which is this 1,528 people. Okay, it's going to be 6 out of those 1,528 people that are actually had a suicide between the age of 10 and 14. Okay, again, you could simplify it. I'm not going to do that for you, but I would suggest you do it in an exam situation. Okay, let's have a look at the next one. What's the probability that a child who died in an accident was between 0 and 4 years old? Now, just be careful now. They're not saying a child chosen at random. They're saying a child that was killed in an accident. Okay, so this is your total. The people that were killed in accidents. That needs to be your denominator. So the people at the accidents at the bottom. Okay, and the number of children in accidents between the age of 0 and 4 at the top. So let's have a look. Where is that information? Let's look and see how many people altogether were killed in accidents. Was 563 people killed in an accident. So that needs to be my bottom number, 563. And how many of those 563 people were between the age of 0 and 4? And you can see that 112 of them were between 0 and 4, 112. So that will be your numerator. Okay, and what is the probability that a case chosen randomly would concern a victim of homicide between 20 and 24 years old? So when they're talking about a case chosen randomly, that would generally be your whole group. okay, and you're looking for a homicide between the age of 20 and 24. So let's look homicide. Let's change our pen color for a change. So homicide between 20 and 24 was 438 people out of the whole group of 1,528. So 438 out of the whole group, which was 1,528. Okay, and again, you could simplify that. Okay. Right, there's a lot of other exercise questions that could be done. This is an example of one of them. The psychologists conducted a study of number of pregnant women. The number were interviewed and assessed for depression and whether they thought their partners supported them. Of the 250 pregnant women, 130 were found to be depressed. 40 of the 100 women who got support from their partners did not suffer from depression. Okay, so first of all, you would need to fill in your contingency table. Sometimes you're lucky and they will give you all the different options and you can actually fill those in. Then, can you see that that's worth 6 marks? So the information that is given to you, obviously if it's in the right place, will get some marks, and then you will actually be able to fill in the rest of the information. That's using calculations like I showed you earlier. So we're not going to actually do these, I just wanted to show you some of the other different bits. And again, you need to look and carefully see what is the language that is used, where are you actually looking for this information. So suffers from depression and gets no support from her partner. So you'd need to then look, we're talking about the whole group here. For all of these questions, they're taking a person chosen at random. So you would always be using this denominator over here. You're using your total. And then you would use, for example, suffers from depression, you would be using one of these over here. And if you were looking for a person that suffers depression and gets no support from her, suffers from depression, no support from partner, that would be your numerator and that would be your denominator. As you go further down, you will notice that it says from those who suffer from depression, okay, and that means that the people that suffer from depression are the ones that you need to have as your denominator. Another nice question that they like to ask is to compare the ratio in its simplest form, and this is where you need to go back and use your table to find out all the information that you actually need. So this isn't really a probability question, but it often is grouped together with probability. So this one says the number of women who suffer from depression to the number of women who don't suffer from depression. So the depression to not depressed would be expressed like that. So for example, if there were 130 women that were depressed and there were only 120 that were not depressed, you would write it like that, and then you would need to simplify, which means that you need to divide both sides of your ratio by the same number. And because they both end in a 0, you can automatically see that you can divide them both by 10, so you would be left with 13 to 12. That's not the nicest. Oops. (13 to 12). Right, so you can see then that a lot of the questions that you have seen not only are probability, they sometimes can relate back to other parts of your math syllabus, for example, number work with your ratios, but they will still use the same contingency table. So you would then be looking at different things that you have actually learned from before. So what I suggest you do is to go and have a look at some of your past papers, have a look at the questions that we've supplied for you, Make sure that you're checking your answers and make sure you read carefully, because most of the time it's not that you haven't got the probabilities correct, it's that you've read the question incorrectly. And that is where this section is so difficult. You need to decide what is your numerator, what is your denominator, and where have I got that information from.